Welcome to our deep dive into the world of machine learning techniques. Today, we'll unravel the mysteries behind classification and regression, two foundational approaches that power much of modern data science. Whether you're new to machine learning or looking to sharpen your understanding, this journey will clarify how these techniques fit into the broader landscape of supervised and unsupervised learning. We'll start by setting the stage with some basic definitions and then gradually explore each method in detail, highlighting their unique strengths and applications. So let's embark on this learning adventure together, starting with the basics of supervised and unsupervised learning. Supervised learning is a core concept in machine learning where the model learns from labeled data. Imagine you have a dataset where each input is paired with the correct output. The model's job is to learn the relationship between inputs and outputs so it can predict outcomes for new, unseen data. This approach is widely used in real-world scenarios, such as email spam detection or predicting house prices. Supervised learning is the umbrella under which both classification and regression techniques fall, making it essential to understand before diving deeper into each method. Contrast to supervised learning, unsupervised learning deals with data that doesn't have labeled outputs. Here, the model tries to find patterns, groupings, or structures within the data on its own. Common applications include clustering customers by purchasing behavior or reducing the dimensionality of complex datasets. While classification and regression are not typically unsupervised, understanding this distinction is crucial for grasping the full spectrum of machine learning technique. Classification is a supervised learning technique where the goal is to assign inputs into predefined categories or classes. For example, a model might classify emails as either spam or not spam. The output is always categorical, meaning the answer is a label rather than a number. Classification is widely used in areas like medical diagnosis, image recognition, and sentiment analysis. Understanding how classification works is key to building intelligent systems that can make decisions based on data. Regression, another supervised learning technique, focuses on predicting continuous values. Unlike classification where outputs are categories, regression predicts numbers. Think of predicting house prices based on features like size and location or forecasting stock prices. Regression models are essential for tasks where the outcome is a real value, and they help businesses and researchers make informed, data-driven decisions. While both classification and regression fall under supervised learning, their goals are distinct. Classification sorts data into categories while regression predicts numerical values. This difference shapes how models are built, evaluated, and applied. For instance, classification accuracy is measured by how often the model gets the label right, whereas regression is evaluated by how close the predictions are to the actual values. Recognizing these differences is crucial for selecting the right approach for your data problem. There are several popular algorithms used for classification tasks. Some of the most common include decision trees, random forests, support vector machines, and neural networks. Each algorithm has its strengths and is suited to different types of data and problems. For example, decision trees are easy to interpret, while neural networks excel with large, complex datasets. Understanding these options helps you choose the best tool for your classification need. Regression tasks also have a range of algorithms to choose from. Linear regression is the simplest and most widely used, but others like polynomial regression, ridge regression, and support vector regression offer more flexibility for complex data. Each algorithm handles data differently, so understanding their mechanics is important for achieving accurate predictions in your regression projects. Let's look at a practical example of classification: email spam detection. Here, the model is trained on a dataset of emails labeled as spam or not spam. By learning the patterns associated with each class, the model can accurately classify new emails, helping users avoid unwanted messages. This is a classic case where classification shines, making our digital lives more manageable. Now let's explore a regression example, predicting house prices. Here, the model uses features like square footage, location, and number of bedrooms to estimate the price of a home. The output is a continuous value, making regression the perfect choice for this task. Accurate predictions can help buyers, sellers, and real estate professionals make better decisions in the housing market. Supervised learning workflow typically involves collecting labeled data, splitting it into training and testing sets, selecting an appropriate algorithm, and training the model. After training, the model is evaluated on the test set to measure its performance. This process ensures that the model can generalize well to new, unseen data, which is critical for real-world applications. Unsupervised learning is often used for tasks like clustering, where the goal is to group similar data points together. For example, businesses might use clustering to segment customers based on purchasing behavior. While classification and regression are not unsupervised, understanding clustering helps you appreciate the full range of machine learning capabilities. To assess the performance of classification models, metrics like accuracy, precision, recall, and F1 score are commonly used. These metrics help determine how well the model is assigning the correct labels to new data. Choosing the right metric depends on the specific problem and the costs associated with different types of errors. Regression models are evaluated using metrics such as mean squared error, MSE, mean absolute error, MAE, and R-squared. These metrics measure how close the model's predictions are to the actual values. Lower error values indicate better performance, helping you fine-tune your models for more accurate predictions. Feature selection is a critical step in both classification and regression. It involves choosing the most relevant variables from your dataset to improve model performance and reduce complexity. Good feature selection can lead to more accurate models and faster training times, making it a valuable skill for any data scientist. Overfitting occurs when a model learns the training data too well, capturing noise instead of the underlying pattern. Underfitting happens when the model is too simple to capture the data's complexity. Both issues can affect classification and regression models, so finding the right balance is essential for building robust machine learning systems. Cross-validation is a technique used to assess how well a model generalizes to new data. By splitting the data into multiple folds and training testing on different subsets, you can get a more reliable estimate of model performance. This method is widely used in both classification and regression tasks to prevent overfitting and ensure robust results. Hyperparameters are settings that control the learning process of a model. Tuning these parameters can significantly improve model performance. Techniques like grid search and random search are commonly used to find the optimal settings for both classification and regression models, leading to better results. For training any machine learning model, data preprocessing is essential. This includes cleaning the data, handling missing values, normalizing features, and encoding categorical variables. Proper preprocessing ensures that your classification or regression model receives high-quality input, leading to more accurate and reliable predictions. In healthcare, classification models are used to diagnose diseases based on patient data. For example, a model might classify whether a tumor is benign or malignant using features from medical scans. These models assist doctors in making faster, more accurate diagnoses, ultimately improving patient outcomes. Financial analysts use regression models to forecast stock prices based on historical data and market indicators. By predicting future prices, these models help investors make informed decisions, manage risk, and maximize returns. Regression's ability to handle continuous outputs makes it ideal for financial forecasting. Classification problems can be binary with only two possible classes or multiclass with more than two categories. For instance, spam detection is binary while classifying handwritten digits is multiclass. The choice affects the model architecture and evaluation metrics, so it's important to define your problem clearly. Some regression problems require predicting multiple outputs at once. For example, a model might estimate both the price and the time to sell a house. Multi-output regression extends traditional regression techniques to handle these more complex scenarios, providing richer insights from your data. In many classification tasks, some classes are much more common than others. This imbalance can bias the model's predictions. Techniques like resampling using different evaluation metrics or adjusting class weights help address this challenge, ensuring fair and accurate classification results. Not all regression problems are linear. Sometimes the relationship between variables is more complex. Nonlinear regression techniques such as polynomial regression or tree-based models can capture these intricate patterns, leading to more accurate predictions in challenging scenarios. Ensemble methods combine multiple models to improve classification accuracy. Techniques like bagging, boosting, and stacking leverage the strengths of different algorithms, reducing errors and increasing robustness. These methods are widely used in competitive machine learning and real-world applications. Just like in classification, ensemble methods can enhance regression models. By aggregating predictions from multiple models, techniques like random forest regression and gradient boosting regression deliver more stable and accurate results, especially with complex or noisy data. Image recognition is a classic application of classification. Models are trained to assign labels to images, such as identifying objects, animals, or people. Advances in deep learning have dramatically improved accuracy, making image classification a key technology in fields like security and healthcare. Time series forecasting uses regression models to predict future values based on historical data. Applications include weather prediction, sales forecasting, and energy demand estimation. Accurate time series regression helps organizations plan ahead and allocate resources efficiently. Feature engineering involves creating new input variables from existing data to improve model performance. For both classification and regression, well-designed features can make a significant difference, turning raw data into actionable insights and boosting predictive accuracy. A key concept in classification is the decision boundary, the line or surface that separates different classes in the data. Understanding decision boundaries helps you visualize how models make predictions and where errors might occur, especially in complex datasets. Loss functions measure how well a model's predictions match the actual outcomes. In classification, common loss functions include cross-entropy, while regression often uses mean squared error. Choosing the right loss function is crucial for effective model training and optimization. Regularization is a technique used to prevent overfitting by adding a penalty to the loss function. Methods like lasso and ridge regularization are common in regression, while dropout is popular in neural networks for classification. Regularization helps models generalize better to new data. A confusion matrix is a tool used to visualize the performance of a classification model. It shows the number of correct and incorrect predictions for each class, helping you identify where the model is making mistakes and how to improve it. Residual analysis involves examining the differences between predicted and actual values in regression. Analyzing residuals helps you detect patterns, outliers, or model weaknesses, guiding further improvements and ensuring more reliable predictions. The ROC curve is a graphical tool used to evaluate the performance of classification models, especially in binary tasks. It plots the true positive rate against the false positive rate, helping you choose the best threshold for making decisions. Missing data is a common challenge in machine learning. Techniques like imputation, removing incomplete rows, or using algorithms that handle missing values can help ensure your classification or regression model remains accurate and reliable. Scaling and normalization transform your data so that features have similar ranges. This step is especially important for algorithms sensitive to feature magnitude such as k-nearest neighbors or support vector machines, ensuring fair and effective learning. Dimensionality reduction techniques like principal component analysis (PCA) simplify datasets by reducing the number of features. This helps improve model performance, speed up training, and make data visualization easier, benefiting both classification and regression tasks. Transfer learning leverages pre-trained models to solve new classification problems with less data. This approach is especially powerful in image and language tasks, where large datasets and complex models are common. Transfer learning accelerates development and improves accuracy. Transfer learning isn't just for classification, it can also enhance regression tasks. By adapting knowledge from related problems, models can achieve better performance with limited data, making transfer learning a valuable tool in many machine learning projects. Automated machine learning, or AutoML, simplifies the process of building classification and regression models. AutoML tools automatically select algorithms, tune hyperparameters, and evaluate models, making machine learning accessible to a wider audience and speeding up development. Ethical considerations are vital in machine learning. Bias in classification or regression models can lead to unfair outcomes. Ensuring transparency, fairness, and accountability in model development is essential for building trust and delivering positive societal impact. The field of machine learning is rapidly evolving. Advances in deep learning, reinforcement learning, and explainable AI are shaping the future of classification and regression. Staying updated with these trends will help you remain at the forefront of technology and innovation. Wrap up: classification and regression are two pillars of supervised learning, each with unique strengths and applications. Understanding their differences, workflows, and evaluation methods empowers you to tackle a wide range of data problems. As you continue your machine learning journey, remember to choose the right technique for your task, stay curious, and keep exploring new developments in this exciting field.